For example number 2, we're going to do one more example of long division, of polynomial long division. And when we're done with finding the quotient, then we're going to talk about how we can check our work. So let's take a look here. Let's find the quotient and check your work for 3x cubed minus 2x squared plus 5x minus 4 divided by x minus 2. So the first thing we tend to do is we tend to rewrite it in that standard notation where we have the divisor on the outside and the dividend on the inside. Okay, and so for the division algorithm, the first thing we're always going to do is we're going to divide. Divide means we're going to take the highest degree term of the divisor and the dividend, and we're actually going to divide them. So 3x cubed divided by x, well 3 divided by 1 is 3, x cubed divided by x to the first is x squared. So the first piece of our quotient that's going to go up here is 3x squared. Now the division algorithm has 4 steps. The first step is to divide. The second step is to multiply. So we're going to multiply this number we put in our quotients position by the whole divisor. So I'm going to multiply 3x squared by x minus 2. 3x squared times x is 3x cubed. 3x squared times negative 2 is negative 6x squared. Okay, so divide is the first step in the division algorithm. The second step is to multiply. The third step is to subtract. And when we subtract, remember that subtraction has this kind of added bonus, if you will, or this is not added, but it has a shortcut of changing the signs. So I'm going to subtract 3x cubed, and when I subtract negative 6x squared, it's going to become plus. So some textbooks refer to this step as subtracting. Other textbooks call this step changing the signs. It's the same. It has the same effect either way. Okay, so when we actually subtract, you know you're doing long division correctly if those highest degree terms cancel each other out. And now I'm going to take negative 2x squared and sum that with 6x squared, and I get 4x squared. And remember, the fourth step of the division algorithm is to bring down. So let's bring down our next term, and our next term happens to be plus 5x. So let's do it again. We're going to loop back around. We're going to continue with this division process until we have a remainder. So let's divide. And again, when we divide, we're going to look at the highest degree term of our dividend, which happens to be 4x squared by this time, and the highest degree term of the divisor, which is x. So 4x squared divided by x is the same thing as saying 4x, and we're going to put that up there in the quotients position. So we took care of divide. Now let's multiply. So 4x times x minus 2. 4x times x is 4x squared. And 4x times negative 2 is negative 8x. So we took care of multiplying. Now we have to subtract. And remember that subtraction is the same thing as changing sign. So this becomes, this is plus 4x squared. It's not going to become minus 4x squared. This is minus 8x. It's going to become plus 8x. These guys cancel each other out, and 5x plus 8x is 13x. And then that last step when we're done with subtracting is then we're going to bring down. I'm going to bring down my next term, which is a minus 4. We're going to continue to do this. We can divide again. Now the way that we know that we don't have a remainder is you compare the degree of your dividend and the degree of your divisor. See over here we have a first degree polynomial, and over here we have a first degree polynomial. If those degrees are the same, that means you can continue to divide. Once the degree of your dividend becomes smaller than the degree of your divisor, then you're left with a remainder. You can't divide anymore, and we'll see that in 1 minute. So we can continue to divide. So 13x divided by x is the same thing as saying 13. So we're going to add 13 over here. 13, and now when we're done with dividing, then we want to multiply. So 13 times x minus 2 is the same thing as saying 13x minus 26. Took care of multiplying. Subtract again means to change signs. So we're going to change signs on both of these guys. This becomes minus. This becomes plus. And the highest degree terms cancel. Again, that will always happen if you're doing long division of polynomials correctly. And we have negative 4 plus 26, which is the same thing as saying 22. Notice this is a 0th degree polynomial. This is a first degree, so we're done. So this 22 is our remainder, and we write that as plus 22 divided by x minus 2. You're going to write the remainder as plus that little bit left over. Now the second part of this, it says to find the quotient, and then it says to check. Now remember that we can check any division problem because the dividend will equal dq plus r, divisor times the quotient plus the remainder. Okay, so up here we have an original divisor of 3x cubed, an original dividend of 3x cubed minus 2x squared plus 5x minus 4. Our divisor is x minus 2. Our quotient is 3x squared plus 4x plus 13. And then we had a remainder of 22. So if the product of these two, if the divisor times the quotient plus the remainder gives us back that original dividend, then we know that we did the math correctly. So let's check. I'm going to put a little question mark there because we're not sure. Okay, so we're going to distribute this into these three terms. X times 3x squared is 3x cubed. X times 4x is 4x squared. X times 13 is 13x. Distribute the negative 2 into each one of these three. Negative 2 times 3x squared is negative 6x squared. Negative 2 times 4x is negative 8x. Negative 2 times 13 is negative 26. And then we have plus 22. Okay, so now we're going to go by and look for any like terms. I have 3x cubed, no other cubic terms. For my squared, we have 4x squared minus 6x squared. That gives us negative 2x squared. For our x terms, let's see, we have 13 minus 8, and that's the same thing as saying plus 5x. I'm done with these guys also. And for our constant term, we have negative 26 plus 22, and negative 6 plus 22 is negative 4. And if you check, look at that. We get back the original dividend. So that is indeed a proof that dq plus r works for this one.